Welcome back. So, where did all this space stuff come from? Where did these meteoroids and asteroids come from? And remember, comets are just asteroids covered with ice. Let's see here. So, all meteoroids and asteroids come from inside our solar system, from our neighborhoods. Not like they're coming from other solar system, other galaxies. Nope, right here. Most, not all, but 99+% of all meteoroids and asteroids formed during the beginning stages of our solar system about 4.54 billion years ago. And they're actually what helped us figure out how old the Earth actually is. Thank you, space stuff. So as far as meteoroids are concerned, most of them are fragments of asteroids that broke apart a long time ago in the asteroid belt. Same with asteroids. So most stuff that comes in our vicinity of Earth is most likely from the asteroid belt. That is a spot between Mars and Jupiter, full of debris. And, the stuff is all jostling and hitting each other, knocking around. And every once in a while, something goes off course, it breaks apart, whatever, and kind of heads our way, head towards Earth. So when we're looking at, for example, an asteroid, all right, or, yeah, let's stick with asteroid. So there's layers, almost like the Earth has layers. Same with an asteroid, because some of these, again, they're 10 meters or bigger, but we're talking kind of the big ones. So kind of the original big chunky stuff from the formation of the solar system. In fact, some of them are so big they even have their own craters from impacts. So you can even slice it in half, and some of the larger ones have differentiated layers. They have a solid, dense nickel iron core, which is just like the Earth. It has a kind of intermediate zone that's a mix between metal, a metallic material, nickel iron, as well as silicate minerals, so rocks. Because the outer layer, see here, the outer layer is a layer of silicate minerals. So silicate minerals, think like quartz and a host of other types of minerals. But in essence, that make rocks. Silicate minerals are very common in rocks. So we have a rocky outer layer, a metal inner layer, and kind of an in-between. So when these were forming, same as the beginning of our solar system around 4.54 billion years ago, just a big collection of stuff, began to differentiate. The heavy stuff kind of sank to the center of the asteroid. The lighter stuff kind of went to the outside. These didn't start off all solid. Stuff was coming together, very hot, molten, before it kind of took shape and cooled down. So that's most of the meteoroids and asteroids that are out there. Now, 99, I can't put a number up, but 99+% of all space stuff, space debris, is meteoroids and asteroids. However, sometimes the Earth gets hit with other stuff. Not meteoroids or asteroids that formed during the beginning of the solar system 4.54 years ago. So other material that hits us is from collision impact debris ejected from bodies such as the Moon or Mars. And these are not as old as asteroid or meteoroids. So the way that might occur is there's an impact somewhere else. Something hits the Moon, something hits Mars, and then stuff is ejected from, for example, the surface of Mars. So that stuff is ejected from the surface of Mars that's floating around space, and sometimes that stuff hits the Earth. Same thing with the Moon. So we found meteorites on the surface of the Earth. Like, wait a minute, what is this stuff? This is Mars. Wait a minute, this is Moon stuff. This isn't normal meteorite material. So we can analyze that stuff. But in any case, when this material is hitting Earth, it's averaging 45,000 miles per hour when hitting the atmosphere. So whether it's, a meteoroid, an asteroid, which isn't too common, or some other space stuff from the moon or Mars or whatever. So when this stuff is hitting our atmosphere, it's hitting it going about 45,000 miles per hour. Now, the atmosphere puts the brakes on a lot of those, burns them up. They're moving so fast, they encounter this atmosphere, which is rich in gases, causing a lot of friction, which heats them up, which melts them, burns them, blows them up, whatever. Most of them. Because 25 million meteoroids enter Earth's atmosphere daily. let me say it again, 25 million meteoroids enter our atmosphere daily. However, most of them are just grains of sand, very minute particles that burn up quite easily in the atmosphere. Every once in a while, something's big enough to hit the Earth. You know, a meteoroid is big enough to where it can sustain all that heat and finally hits the Earth. Well, it's rare that we get asteroids. That would be a large impact event, a lot of destruction and deaths, etc. So those aren't too common. But in any case, yeah, 25 million meteoroids enter our atmosphere daily, but that's okay. Most of them burn up. They're just little grains of sand when they enter the atmosphere. So if this stuff does make it to the ground, we call it a meteorite, right? Meteoroid, space, meteor, the flash of light in the atmosphere, meteorite once it hits the ground. If the space debris does hit the ground, we call it a meteorite. And there's three types. There are stony meteorites, there's iron meteorites, and then stony iron meteorites. Stony meteorites, an example of those is a type of meteorite called a chondrite. These are the most common type of meteorites. These are the most common type of space debris that you would find. They form from the outer layer of that asteroid. Remember that outer layer is a stony crust. The hard metals in the middle, in between is kind of a mix between both. When asteroids kind of collide in that asteroid belt, fragments of them go flying off into space. This is that outer crust of the asteroid. Typically, you'll see this black, what's called a fusion crust on a meteorite. If you pick it up, you're like, oh, it kind of has this kind of burnt look to it, maybe some cracks, like a cracked eggshell. It will be magnetic. All meteorites are magnetic, but just because something is magnetic doesn't make it a meteorite. That makes sense. There are rocks that are magnetic, but if you think you found a meteorite, the first thing you do, put a magnet on it. If it sticks, it's a meteorite. If it doesn't stick, it is not a meteorite. So again, the chondrites contain grains of rock called chondrules. And the chondrules predate the Earth and give the solar system the age. So it's this type of kind of stuff we can analyze, looking at the small little pieces of rock that make up this stony meteorite, analyze it and look to see how old it is, giving us some information about the early beginnings of the solar system, when it was just a bunch of little stuff, a bunch of little specks floating out there in space. And that's what all these little chondrules are, those kind of initial little bits of the solar system forming. So that's what we see if we were to slice one of these in half and look at it on the inside. All these little specks are chondrules, the very beginnings of minerals and rocks from the beginning of the solar system. So that's the outer layer of an asteroid when it's kind of crushed, and this is the most common meteorite type that we see. Iron meteorites, that's the second classification, about 90 to 95% iron. The rest is nickel and some other elements. This is from the core of an asteroid, very dense, very heavy, very strongly magnetic. So again, all meteorites are going to be magnetic. What's interesting is because this iron-nickel mixture formed in space where there's no gravity, when this material cooled, it allowed it to grow these interesting crystalline patterns for a cooling metal that can only exist in space, can only exist if this metal cooled where there's no gravity. If we heated up a bunch of iron and nickel here on Earth and then let it cool down and then cut it open, we would not see this. This crystalline pattern to metal, to this iron-nickel alloy, only forms in space where there's no gravity. It would not form here on Earth. So that so if we slice open some iron meteorites and kind of polish it and do some fancy things to it, we get to see this crystalline pattern called Widmanstätten texture. So we have the stony meteorites from the outside of a crushed up asteroid. We have the iron meteorites from the center of a crushed up asteroid. But then there's that in between. There's that in between area of an asteroid, and the type of meteorites that we get from there, that originate from there, are called stony iron meteorites. One example is called a palisite. These are the least abundant of all meteorites that we find here on Earth. Only 2% of all known meteorites are this type. So it has equal parts metal, nickel and iron, and stone, chondrules. So it's kind of like a half and half, again, because it's coming from that in-between area of that asteroid, that boundary between the crust and core of the asteroid. It is also slightly magnetic. Again, all meteorites are going to be magnetic. So what's cool, when you slice this one open, we see the mixture of the iron, the metal, as well as the chondrules, the little bits of minerals and rocks. So it kind of gives it a very interesting texture. And if it's sliced thin enough, the light can come through these. So as far as if you're ever looking to purchase meteorites, for the stony meteorites they're the most abundant, so they're the cheapest. The iron meteorites are kind of in the middle, but the stony iron meteorites, like this thing here, are very rare, so those are typically the most expensive. FYI. So now, sometimes when things hit the ground, meteorites, there's some other material that's formed from Earth, not from space, from Earth, that sometimes people get confused about, that they think that is the meteorite. And then one example is called tektites. Tektites are glassy objects formed from ejected molten debris material after a meteorite impacts, and these can be scattered widely throughout the area. So depending on what type of material the meteorite impacts, a lot of heat, a lot of pressure, it's going very fast. So depending on the type of material that it hits, it can turn the areas, some of the material in the area molten, so liquid, liquefy rocks or dirt or sand. And as it cools very quickly after its molten state, it forms this kind of glassy type texture. So a lot of this kind of is very glassy in nature. You can kind of see it looks like glass. You can actually see through some of these. But it depends on what the material hits. But you can find these kind of scattered around an impact site. And what's cool is based on the size of, or excuse me, based on the shape of the tektite, you can kind of figure out how far away it is from the impact area. So you can actually use these to trace it back to where there might be an impact, which could be helpful if the impact happened millions and millions of years ago. Maybe a lot of that material has been filled in, weathered, and eroded away, but if you can find some tektites, you can kind of follow it back, following their patterns back where you can kind of see where it is. The original impact. So you get an impact, it's molten material, shot up and out. And again, based on how far it is away will dictate the kind of shape that it takes as it begins to cool. So if you're looking at kind of like these kind of elongated blobs, so it's going to be relatively close. Kind of splash form tektites, so relatively close, but you can kind of see how the shapes of these kind of change as you get further and further out. So again, looking at some of these, blobby things, these are going to be more indicative of things found closer to an impact site. So not everything that we find in an impact site is actual space debris. Again, this stuff is just actual Earth material that's been melted and ejected out. It cools in the air, slaps and hits the ground, and that's what you get. All right. So that's a little bit about space debris, talking about asteroids and meteoroids, and then when we're looking at meteoroids, meteors, meteorites, different types of meteorites, all kinds of fun stuff. So anyway, so that's just kind of setting the table, giving you some background information on space debris, some of the stuff we need to worry about. So when we come back for section 2, we'll talk about the actual threat of impacts. Again, most of the stuff that enters our atmosphere is very small. It burns up, but when it gets a little bit bigger, what's that threat level of those big things? That's where we're going to go next. I'll see you back here in just a second.